Yeah, I guess this is really like this is a big debate, right? In the philosophy of science is like, let's just grant for the sake of argument that there is the world as it actually is. Let's just pretend that that is a concept that we can talk about. And then we talk about the world of experience. There's the world as we experience it through our senses, and maybe we extend that even to our scientific instruments. And the question is, are these the same? Do they map onto each other? How do they map onto each other? These are the kinds of questions that we're asking. And so a good story to tell here, I think a story that's quite useful to tell, is the story of gravity. Okay, let's start from 2000. So 2,000 years ago, Aristotle says something like, things in the cosmos have a destined place of rest. And that's why they fall. They fall because they have a destined place of rest. 2,000 years ago, people didn't really, this is also kind of an interesting point, people didn't really conceive the motion of things on the surface of the Earth like an apple falling. They didn't think of that as being the same type of phenomenon as the planets moving in the sky. All of these things were happening according to a kind of, structure or form of the universe that the universe was kind of filling through time. And there are all these, classical debates about this question. Okay, so fast forward 2,000 years into the 17th century, you come into like a European context where people are very interested in, machinery, and there's this new phase of scientific skepticism. There's the Protestant Reformation, and you get people who basically come to the conclusion that the universe is a big clock. Okay, so kind of the same as the classical idea. You've got the universe is like a big machine, and gravity is a mechanical phenomenon. So one of the theories, for example, of how this might work is that passing through us from all directions are tiny little particles, and we don't perceive them because they're very small. But these particles bombard objects like the Earth, which are quite massive, from all directions equally. And the sun occludes the motion of the particles from that direction. And so the net force of the particles is to push the Earth into the sun. That's the mechanical theory of gravity. And people really thought that some version of that was going to turn out to be correct. And then Newton, who also believed in this, by the way, said, well, I can't really make it work with this theory of the little particles, but if I just imagine that there's a mystical force, the force of gravity, I actually get all the predictions right. Like if I imagine that there's this mystical force, I can rederive Kepler's laws of motion, and I can tell you exactly where the planets will be given their positions at this moment in time. And amazingly, I can connect the motion of the planets to the motion of an apple falling from a tree. So actually that apple falling from a tree, that's the same type of phenomenon as the moon orbiting the Earth. So that's a great breakthrough. And then we say, okay, we've arrived at the story of science. And some time passes, and it begins to become clear that there are aspects of this story that are sufficient. For example, there's a phenomenon, very famous phenomenon, the precession of the perihelion of Mercury. So this is a phenomenon in the orbital mechanics of Mercury around the sun. And Newton's theory of gravity just doesn't explain this phenomenon. So then Einstein comes along, and Einstein proposes a new theory of gravity. He says gravity is not about mystical forces. There are no mystical forces involved in gravity. Gravity is about geometry. So everything in the universe is trying to follow a geodesic. It's trying to follow a straight line. And mass and energy curve space and time so that a straight line for an object moving through curved space-time appears curved, like an orbit, for example. And this theory ends up explaining not only the precession of the perihelion of Mercury, but even, for example, the way that light bends around massive sources of gravity. So, for example, if you look at the position of stars in the sky, and then you wait until some massive object like the sun comes between you and the stars, the position of the stars will appear to shift. And that's in Einstein's theory due to the fact that light, even though it has no mass, is following a geodesic in space-time and curves around the mass of the sun. So great. Now we have a new theory. It's totally different from Newton's theory, which is totally different from the mechanical theory, which is totally different from Aristotle's theory. It's more predictively powerful. Is this theory the truth? Is this theory describing the world as it actually is? Well, we know that this theory also has its limits, right? We know that there seems to be some really fundamental set of problems when it comes to unifying this theory and making a cohesive story between this theory of gravity and our theory that describes small particles in the universe. And so the solution to that conflict might be a whole new way of thinking about the universe and about gravity. And now, will that be the one? Will that be the story? And you can kind of see the problem here is that each time we come up with a new story, that story relies psychologically on very different concepts. We went from mystical forces to geometry, and then maybe on to some new theory in the future. And there's a position which I think is kind of fun called pessimistic meta-induction. And basically this theory says, yeah, this is just going to keep happening. You're just going to keep going and making more theories. And, your theories will get you good experimental results and you'll refine your ability to predict experiments. But the story you're telling doesn't need to have any bearing on, quote unquote, the world as it actually is, if that is indeed a well-defined concept. And so this is kind of an interesting view, I think, on science.
So if you read Jaynes's book, in the first chapter, he has like he has like a little section called Analogies with Physical Theories, because this is his book on plausible reasoning, like the logic of science. And what he says is, what we do in physics is we try to model things. And when the models get more accurate, I'm paraphrasing here, this is not an accurate retelling of what he says, but when the models get more accurate, or we're able to reproduce predictions for more and more observations that we previously couldn't predict correctly, then we say that we've made progress, right? And this is this process that you've said, like every time we make progress, every time we have a new theory, we make better predictions, and we're happy with that. And he goes on to say, no one knows whether this process will ever end.
Yeah, this is called the end of, I guess, is this asymptote. And the other phenomenon here, right, is that as we learn more about the universe, we can ask more questions that are more specialized. And so it does feel, I think, especially, today in physics, looking back on kind of the scope of the history of physics since the mid-17th century, it does feel like as if we're getting into finer and finer grades of minutia and more specialized fields that are harder and harder to connect with other fields, just because practically it's hard to have enough knowledge to be able to see the connections between this sort of burgeoning frontier of understanding. It's hard to be an expert in one particular part of quantum mechanics and then also an expert in some particular part of soft condensed matter physics. And, these branches are really spreading out in a way that makes it difficult to find. It doesn't mean that unification doesn't happen. It just means the sort of process gets more and more difficult as we go along.
And so like one thing that I just want to backtrack on and sort of double down on is this idea that when you see popular like science populists talking about why can't I speak? Science popularizers when they speak about general relativity today. They talk about it, this is the way the world works, right? But they're also very clear that there are issues with general relativity in our understanding of gravity. And from a historical perspective, it's very clear that if we do improve upon general relativity and we do start talking about and improving upon its predictive power, that might come in the lens of some new type of theory that recovers all of the predictions of general relativity. Like general relativity recovers all of Newtonian mechanics and specific limits that are, of course, you want that to be true. But then it might come with a completely different conceptual framework and a completely different story that we tell ourselves to understand this conceptual framework, right? So like like the revolution in gravity might not preserve the story that we're telling ourselves today about gravity.
But it will, this is an observation that they sometimes call epistemic structural realism. So this is the idea that, so in philosophy, right, epistemology is about your state of knowledge, and ontology is about the state of the world as it is. So when we talk about the actual world, insofar as that's a concept we can talk about, we're talking about something ontological. When we talk about our knowledge of the world, we're talking about something epistemic. And so epistemic structural realism says that the mathematical structure of these theories, as you say, is preserved, kind of nested within these bigger structures that we keep adding to improve the predictive power of our theories. And it is this structure which is real. So the epistemic structural realist wants to say something like that structure that we're building, that mathematical structure, whatever stories we might be telling to help ourselves remember how to put the symbols on the page, it's that mathematical structure that represents our knowledge of reality. And sort of grows monotonically.
Would you disagree with that though? Because that's basically what seems to be happening, right? Like we're making predictions, we make experiments, we see what's happening in experiments and we do these experiments, in different regimes and different, scales of different things, and our theories are able to, in certain limits, and not like from the human perspective, these limits are extremely wide. What we're able to predict, like the areas that we're having difficulties with, seem very extreme to me at face value. So what you just defined as what was epistemic realism, that does seem to be what the project of physics is.
Well, I think that the philosopher would say, I think that if you're a physicist, you're quite happy with the statement of ESR, because that's what's happening. It seems like, you do it in class, you do the sort of the low velocity Taylor series expansion for the kinetic energy and special relativity, and you get out the kinetic energy from classical physics. And, that it just seems obvious that that's what's happening. The critique of ESR, as I understand it, is the R part, is the realism part. So the question is, how much is this reflective of reality as it is? And this is where we begin to get into this sort of split between realism and anti-realism.